Okay, so that's, we're reviewing, right?
Yeah.
For the final, and what are you guys doing tomorrow?
Question.
Okay, yeah, good. Come up
You
with
said you could have questions.
questions.
We did that.
Oh, yeah, not tomorrow, Friday. Yeah, tomorrow you're doing lab.
We what?
Tomorrow you're doing lab.
Oh, yeah.
Yeah.
Yeah, not
Friday.
tomorrow, Friday. Okay. I knew what he meant. Yeah.
Okay. So here's the topic. We went through some of these yesterday, or just kind of mentioned it. We didn't really do any example problems, but we'll just write up a short list. Okay. So we have vectors. You have kinematics. You have Newton's second law, which I guess Newton's law is really. You also need Newton's third law, of course, for these types of problems. So, but really we want to apply this. Rotational motion. Or circular motion, maybe. I'll put circular. Then we did statics. We did energy and work. We did momentums and collisions. Eight, simple harmonic motion. And springs. Okay. Then we did waves. Fluids. And then finally, thermo. And so these are what we covered this semester. And so all you have to do is know those things. You're good. It's not that bad, but maybe we can get some reviews. The type of question I'd ask for vectors. I'll give you a type of question. So, and this is, I'll just give you an example problem. And we can go over a couple of these important example problems. I'd like to go, I think the most important things to cover are probably things like this, kinematics is important. These are kind of applications of Newton's second law. And then the statics a little bit more of torque, so this may be more important, although I might do a circular motion problem, I like that, those problems.
So basically.
Yeah, but these are some example problems that I'd like to do. There definitely will be a Newton's second law and a kinematics problem, and vectors or something you have to do. There definitely will be a thermodynamics problem. And then the other ones, are probably hit and miss, okay? There'll probably be about 8 total problems, so I'll take 2 of your problems.
Only 2.
How about you take 8 of our problems?
I say 4.
4 because
Yeah.
you're doubling them.
Yeah. I say 4. Come on.
I mean, if you just let us write the test, then you don't have to do it.
You know, you guys don't do any better on the problems you write than the ones I write.
So you should take 8 of them then.
So,
That's me.
it's true though. True, yeah, last test, for instance, the second problem which you guys wrote was the hardest problem, was the one that was the worst. So I don't know what you guys, yeah, I don't know. I'll tell you what, seeing as that's the case, I will seriously consider putting 4 of those on.
Okay, sweet.
But depending on how good your problems are, two at least, if they're very good problems, maybe 4. And I may do less than 8 problems if the problems are a little bit more involved. Okay. I'll aim for the hour. I will aim for 1 hour and 40 minutes though. Okay. So. Vectors, let's do one. Let's say R1 is a position vector. Let's say that a person traveled 10, let's do 10 miles at 30 degrees north of east, and then turn directions and travel a second distance, 20 miles, at 30 degrees west of north. So question would be, A, what is the final distance from starting point? What's the direction? Is direction from starting point of the final position? Okay, so this would be a good kind of review of vectors. So how do you start a problem like that?
By drawing a picture.
Yeah, that's usually the best way to start. We'll go ahead and do that. So, let's start. Origin right here. So let's say that this is the east direction, north direction, west, south. And I can call the east direction the x direction, the north direction the y direction. It's usually a good starting point for these direction ones. Okay, so the first one, R1, 30 degrees north of east. That means that R1, I'd write it as a vector here, and this would be 30 degrees in that direction. And then the length of this is 10 miles. Okay, then you add the second vector to it.
30 degrees west of north.
30 degrees west of north. So if I put this final thing here, R2, it looks like that, right?
Mm-hmm.
Well, I'm going to actually just draw R2 from here and then add those 2 vectors up.
Okay.
Okay? So, well, I can do it. I'll do this. R2. Sorry, it kind of goes through everything. 30 degrees here. And it's pointing, it's 20 miles long. So I have to add these vectors. What do I want to do?
The components of each.
So so this is R1, R2 is with this. R1. Okay, so how do I get R1?
Break it into components.
Yeah, so R1 vector. So R1 goes over this distance in the x direction and up this distance in the y direction. So what are the components?
Cosine of 10 cosine of
10
30.
miles. Cosine of 30 degrees.
Is in the x
X hat. Good. Plus
10 sine of
10 miles. Sine of 30 degrees. Y hat. Good. How about R2?
20 miles.
20 miles, good. And 20 miles starting point.
Do you do negative?
How much is in the X direction?
It's negative.
You're right. So it goes this amount over in the negative X direction, right? So this distance is sine, 20 sine of 30 degrees. You see that? So I'm going to do, and it's in the negative X direction, so 20 miles sine of 30 degrees X hat, good.
Wait. How is that a sine?
Because this is the opposite side to this angle.
Yeah. Sorry.
So remember, X is not always cosine,
Yeah.
Y is not always sine. You have to look at the problem.
Plus 20 miles.
Good. So this is plus
20 miles.
20 miles cosine of 30 degrees Y hat. Okay, so R1 plus R2 is going to be the final position here. And that's what I wanted to get. Yeah, 10 miles cosine of 30 minus 20 miles sine of 30. So this would be, well, so it'd be 10 square root of 3 over 2. Because cosine of 30 is square root of 3 over 2. You could use your calculator, don't worry. Minus 10 X hat because sine of 30 degrees is 1/2. And then plus 5 miles from here, Y hat, plus 20 square root of 3 over 2, Y hat, and that's miles. So if I do all of that, what do you get? It's 10.
Is that over X hat?
No, just times X hat. That's, the X hat tells me how far in the X direction it goes. X hat's a unit vector length 1. So it's pointing in the X direction. So if I multiply it by whatever it multiplies is how far it goes in the X direction. You get an answer?
When I did it, I got negative 1.33.
Negative 1.33. Yeah, it'll be, should be that. Should be negative. Minus X hat, good. And then how much in the Y hat grade?
I got 22.3.
That's 22.3 minus Y hat. So the points, just like this, right? Just a little bit in the X direction, then the negative X direction, mostly in the Y direction. Okay. So how far, how long is it? What's
Do
the
the
magnitude of our
Pythagorean theorem.
How did you get that?
Huh? You do Pythagorean theorem? Oh, yeah.
Pythagorean theorem on these two numbers, right? So it goes, this is a right triangle. Let me see this. So this is my vector. How much it goes in the X direction, Y direction, how much it goes in the X directions form a right triangle. And so I take this squared plus this squared square root. So square root of 1.33 squared plus 22.3 squared. And then the units would be miles. No, it's about 22.3, right? 20, maybe 22.4. When you get,
It is 22.3.
yeah. That just happens that, you know, if you had something big squared plus something small squared, take square root, this thing really doesn't matter much. And then what's the direction you travel? Doesn't matter with the direction.
So do you do the, find out the angle?
Yeah, direction. Yeah. So I'll do it over here. So the direction, if I want to get this angle, that's one way you could do it. You could have this angle, just label how you do it. And if I want to get west of north, I'd look at this angle. And how would I get that angle?
Tangent.
So the tangent of that angle is this distance over this distance. So tangent of theta is 1.33 over 22.3. So how would I get the angle?
Doesn't it negative matter or no?
No, because I'm just looking at the lengths. I'm going to add in the
Isn't it
negatives
negative
as
1.33
west of
though?
north.
Oh, okay.
Okay.
Isn't it like on the other side of the y-axis?
Yes. So the y-axis is up like this.
Oh,
The thing's like this, so it'll be
Oh.
west of north.
yes, okay.
We're going 30 degrees north of here, we're going 30 degrees west of north. That makes this a right triangle over here.
Yeah.
You've got 10, you've got 20. We're going to square those up.
No, this isn't the right triangle. Okay.
Yes, you're 30 degrees north of east, you're 30 degrees west of north.
Actually, maybe you are right.
So why would
That was an accidental right triangle. Okay.
10 squared plus 20 squared?
Should give you this. Okay. Go give it a try to see. Yeah. Good check, by the way. So tangent to the minus 1, 1.33 over 22.3. Okay, and that, whatever that angle is.
3.4.
3.4 degrees. Okay, so you get, so you'd walk 22.3 miles, 3.4 degrees west of north.
West of north.
So when you ask for the final distance, you're wanting it,
The magnitude
okay.
is the distance. Yeah, that's a good thing to notice. That was accidental. I'm coming up with a problem. Yeah, you can check it though. Okay, so kinematics. Let's do a kinematics problem and then we'll do a Newton's second law problem. Those are good things to remember. And then hopefully these, I'm kind of focusing on the back ones. I hope these ones are more recent in your memory, okay? Actually, since I'm running out of time, I'd like to do, I'm just going to do a circular motion problem, and it'll involve Newton's second law. Kinematics is mostly projectile motion. We did a bunch of that in lab, okay? I'll write this problem though for 2, and I won't do it, but see if you can get the answer to this. And then I'll post up the answer online, online. So 2, let's say I have a cannon, a ball that's fired off of a table or a cliff of some sort. Say this is 2 meters, fired from a height of 2 meters at 50 meters per second at an angle of 10 degrees above the horizontal. A, what's the range? Question mark. And then B, what's the maximum height that the projectile got up to above the ground. So that would be this height here. And then C, time in the air. This would be the range. Right? So I'll post up a solution to that one. See if you can get that on your own though. Okay?
Okay.
That's a good practice. And then
That's for kinematics, right?
that's for
Yeah.
kinematics. And then finally, let's do the Newton's second law one, which involves circular motion. This is a tricky one. Might as well go through it. Let's say I have a race car moving around a circular track. Say this circular track is R. Okay, and let's say that the speed is V. All right, if I look at the cross-section of this track, so I'm facing along the car, what I would see is the track is banked at some angle. Track is banked. The angle that it's banked at, so that the car is traveling this way, so I'm looking at it like along the track from that direction. The angle that it's banked is at, let's do something not too crazy, let's do 20 degrees. Okay. And there's a friction force of 0.9 between the track and the tires. Question is, what is the maximum speed V? This is mass M. What is max V that this thing could go around the racetrack? Now this is a pretty complicated problem. Let's see if we can do it. Can I erase this kinematics one? All right, so what's the condition to move in a circle?
Centipede. Acceleration. Oh, sorry. Acceleration is 0. No.
Acceleration 0 to be moving in a
No.
circle?
No. It's a v squared over r or something. That equation, you know.
It's the acceleration, right? It's v squared.
Yeah.
It's v squared over r pointing towards the center of the circle. So that means that the acceleration in this direction, the magnitude of that a has to be v squared over r. You see that?
Mm-hmm.
So if I'm looking at this thing moving around the track, the acceleration towards the center of the circle, which is, points like this, also points like this if I'm looking at the track, that has to be v squared over r. Make sense? Okay, let's go ahead and see if we can understand this picture here very carefully. It's a block on a plane, but it's not quite, but the acceleration isn't down the plane. Okay, the acceleration has to be, what's that?
You don't know acceleration.
Well, yeah, we're going to have it sitting here, but there's actually an acceleration this way, towards the center of the circle.
It's got to equal out because you're not sliding down the track.
You're not sliding down this, you're not sliding this, you're not sliding up the plane, but there is an acceleration
Towards the center.
towards the center of the circle. So this is slightly misleading as a block on the plane problem, because I have to note this, there is an acceleration here. So, what do I know about the sum of forces on an object?
Equal to MA.
A, okay? I'm going to look at this example, and I'm gonna introduce a coordinate system. Let me draw a free body diagram. So, what are the forces on this block? On this car? Gravity going down. I'm gonna write this as just mg. Normal force going upwards. If I'm looking at
Acceleration.
maximum speed to move around the track, that's a little tricky as far as friction is concerned, but if I'm at my maximum speed, if I go any faster, I'll slide up the track, right? So that means that my friction force will actually be pointing this way, down the track. And the sum of all these forces has to be equal to what?
Here.
MA. Right? So let's go ahead and sum up these forces. This, by the way, this angle here, 20 degrees. I know that because at 0, if the track were banked at 0 degrees, the normal force would point straight upwards. Also, this friction force, if the track were banked at 0 degrees, which way would it point?
The other one.
It'd point that way, straight that way, right?
So this is 20 degrees.
So, where's the 20 degrees on the friction force?
Between the top and the force.
That's right, 20 degrees. If the track were banked at 0, the friction would point directly that way. That make sense? Yeah.
Can't you just make your X and Y axis tilted and then add it?
Usually for block-on plane problems, you want to have a tilted axis. And that's because the acceleration is down the plane. Unfortunately, in this situation, well, we could do it. I'm just going to add up these vectors, okay? And I hope this isn't misleading you for all other block on the plane problems. We're just ran out of time. I want to add up, well, shoot, I'm going to run out of time now. Now let's go ahead and just do this quick, okay? So, 8 points in that direction. I'm going to call that, I'm going to call that the X direction. Doesn't matter what I call it, as long as I'm consistent. You guys see if you can do it your way, by the way, and see if you guys can get this answer that I'm going to get, okay? So, friction force, cosine of 20 degrees, sum of forces in the X direction, are going to be friction force, cosine of 20 degrees, plus normal force times
Sine
Sine.
sine
of 20
of
degrees.
20 degrees, good. And that's equal m v squared over r, ma. This friction force, by the way, is mu
Plus,
S
do we have to add
times
mg?
n. What's that?
Don't you
No,
have to
not
add-
that's in the Y
or
direction.
that-
Oh yeah, but what is the mg just?
Aren't we doing
Is it not
X?
divided into 2 components?
Straight down.
Oh, it's just
And we
straight
haven't
down.
tilted it.
It's
Yeah,
just
so
straight down.
if we're doing x this way, y like this, okay?
Oh, so it's just y.
Normally on a block on a plane, you tilt it, but not in this circular motion case. You can't, it doesn't matter what you do. You could tilt it, but then you could tilt it if you wanted to, and then split up the A into x and y directions. You just have to add up vectors and set the result equal to MA. Let's do sum of forces in the y direction. So here I have normal force, sine of 20 degrees, minus friction force, sine, or normal force cosine actually, isn't it? Minus the friction force, sine increase minus mg is equal to 0 if it's not moving up and down the y direction. Make sense?
Mhm.
Make this mu s n. Okay, so here's what I don't know. I don't know what n is, and I don't know what v is. Everything else we're assuming we know. Go ahead, and we don't know what mass is, but you'll see that cancel out. Go ahead, and we'll post up the key later, I guess, for this. Go ahead and see if you can get what the v is. Good practice problem. And if you want to do a tilted coordinate system, go ahead. You're just going to have to split up that A into different
Yeah, it is. So like, is this combining the Newton's second law plus circular motion?
Some examples. This is definitely a hard problem if you've ever seen it.
Yeah. Okay.
But it's a good review. That's what we did when we did this one.
Okay.
But then we can do this one, we can do that one.
I had a teacher back in high school
Well,
with that
no.
mentality.
What's
What?
that?
I had a teacher back in high school with that mentality.
What's your problem?
Always teach harder than what you're going to put. We just
Oh yeah, a problem. We did not copy it from you, by the way.
It's okay.
Yeah.
Where you wrote
Yeah.
our problem, and it's almost the exact same as what you talked about.
Yeah. We wrote a vector. We wrote a vector problem yesterday, and you started saying that, and I'm like, that's like almost our problem. But it's cool.
Just use-
Ours is cooler.
Okay.
Ours didn't go in the negative wall.
Oh, that's okay. You
Yeah, I didn't.
Just do what you want to do.
Okay.
No big deal.